A mechanical oscillator is formed by a block S of a mass m. So the mass of the block S is m, and a spring of negligible mass, we do not consider the mass of the spring, and a spring constant or a stiffness K. S is attached to one end of the spring, as we see in the figure. So the spring is attached from this side to S, to the block, and the other end of the spring is connected to a fixed support A. This is the fixed support A. S can move without friction on a horizontal surface, as we see in document 1. This is a horizontal frictionless surface. Our aim from this exercise is to determine the values of m and k. Given at the equilibrium, the center of mass G of S coincides with the origin O, so this is at equilibrium. S is displaced horizontally in the positive direction, which means to the right. At instant t0, the abscissa of G is x0, and S is launched in the negative direction with an initial velocity v0 equals v0i, where I is the unit vector of the x-axis. At instant t, the abscissa of G is x, and the algebraic value of v of the velocity is x prime, or dx by dt. The horizontal plane containing G is taken as a reference level for gravitational potential energy. So if we go back to the system, we had the block S connected to a spring connected to a fixed end, which is A. So this was the equilibrium position. As you see, since the whole system is on the horizontal, then there is no change in GPE, or gravitational potential energy. Right at instant t, the expression of the mechanical energy of the system oscillator Earth in terms of x, m, k, and v. The mechanical energy is equal to the kinetic energy plus gravitational potential energy plus elastic potential energy. As we said, since we don't have a change in height or in position with respect to the reference, then there is no gravitational potential energy. Then the mechanical energy is equal to Ke, which is 1 over 2 mv squared, plus Pe elastic, which is 1 over 2 kx squared. This is the solution. We found the mechanical energy in terms of x, m, k, and v, as you see. Establish the second order differential equation in x that governs the motion of S. First of all, there is no friction. No friction indicates that the change in mechanical energy over time is equal to 0. Now, the mechanical energy, we found it as 1 over 2 mv squared plus 1 over 2 kx squared. I will rewrite the same formula by replacing v by x prime, because v is given as x prime, or the first derivative of the position, plus 1 over 2 kx squared. Now, if you wanted to find d of mechanical energy by dt, so d by dt of 1 over 2 mx prime squared plus 1 over 2 kx squared is equal to 0. Why? Because we replaced in this formula me, we replaced its form in this formula. So dme by dt equals 0. I took the same thing, but instead of me, I wrote its form. Now, we will get 1 over 2. I'm doing the derivative for the first part. X prime squared becomes 2 mx prime x double prime plus 1 over 2. Now I'm working on this part into kx squared, so it becomes 2 kx prime equals 0. 1 over 2 into 2, it becomes 1, so I will have mx prime x double prime plus 1 over 2 times 2 gives 1, kx x prime equals 0. Let's cross out. So x prime and x prime, they cross out. I will get mx double prime plus kx equals 0. I rewrite it so it becomes x double prime, divide both sides by m, plus k over m, x equals 0. This is the final answer. We have to do the whole derivation. Deduce the expression of the proper angular frequency omega 0 of the oscillations in terms of m and k. We found the second order differential equation as x double prime plus k over m x equals 0. Now, the general formula is x double prime plus omega 0 squared, the proper frequency, proper angular frequency, x equals 0. Now, if we compare both equations, we can deduce that omega 0 squared is equal to k over m, or omega 0 is equal to radical of k over m. The solution of the obtained differential equation is x equals xm sine omega naught t plus phi, where xm, omega naught, and phi are constants. Write the expression of v in terms of xm, omega naught, phi, and t. We know that v is equal to the first derivative of the position. So we have to find the first derivative for this function. We will get xm omega naught cosine of omega naught t plus phi. This is the solution for this part. So we did the derivative, the first derivative for this function. Xm is constant, we keep it. Sine omega naught t plus phi, it becomes omega naught. Phi is constant, its derivative is 0. So omega naught, this is t, the order 1. We get omega naught out, it will become cosine omega t plus phi. Find the expressions of x naught, v naught in terms of xm, omega naught, and phi. So we have to consider the instant where t is equal to 0 seconds. We will get x0 is equal to, I will write the original form first, xm sine omega naught t plus phi. So if we replace, it will be at t equals 0 xm sine of 0 plus phi, which means that x naught is equal to xm sine phi. Now, for v naught, okay, we got the formula for v as xm omega naught cosine omega naught t plus phi. So at t equals 0, it will be v equals xm omega naught, this will be v0, cosine of 0 plus phi. Then we get v0 is equal to xm omega naught cosine phi. Okay. Deduce that xm equals this form, x0 squared plus v0 squared over omega 0 squared. From the previous part, we got x0 is equal to xm sine phi. And we got v0 is equal to xm omega 0 cosine phi. From the first equation, we can get that sine phi is equal to x0 over xm. And from the second one, we can get that cosine of phi is equal to V0 over xm omega 0. We will use the trigonometric function sine squared of the angle phi plus cosine squared of the angle phi is equal to 1. So we will replace there. It will be x0 over xm all squared plus v0 over xm omega naught all squared is equal to 1. So the equation will be x0 squared over xm squared plus v0 squared over xm squared omega 0 squared equals 1. Okay. We're looking for xm. xm is in the denominator of the fraction. So if we multiply both sides of the equation by xm squared, this will cross out, this will cross out, we will get an xm squared there. So multiply both sides of the equation by xm squared. It will be xm squared multiplied by x0 squared over xm squared plus xm squared multiplied by v0 squared over xm squared omega 0 squared equals 1. Now we will cross out some factors. Now xm squared crosses out with xm squared. Same thing goes there. I did a mistake, I will fix it now. This is not 1, this is xm squared. Xm squared times 1 is xm squared. Now we will get x0 squared plus v0 squared over omega 0 squared is equal to xm squared. Square root or radical both sides, you will get radical of x0 squared plus v0 squared over omega 0 squared is equal to radical xm squared. So take it out of the radical, you will get xm is equal to square root of x0 squared plus v0 squared over omega 0 squared. This is the solution. We deduce that, or we prove that it's equal to this form. An appropriate device traces x and v as functions of time as shown in documents 2 and 3 respectively. So the first document, document 2, traces x, the position versus time, and document 3 traces the velocity v versus time. Specify the type of oscillations. As you see in the second document, document 2, the position is ranging between two fixed points all the time. Or if you check the velocity, the same thing happens there. It's ranging between two limits or two fixed points all the time. So what is the type of oscillation? What is the indication mainly from graph 2? It means that the mechanical energy is conserved. So we have no friction, so the oscillations are undamped. So the answer should be, the type of oscillations is free, undamped, mechanical oscillations. Indicate the values of x0, v0, xm, and vm. x0 is the position at t equals 0. v0 is the velocity at t equals 0. xm is the maximum value of the position, and vm is the maximum value of the velocity. Let's start with x0. At t equals 0, this is the position versus time graph. At t equals 0, it was at 10 centimeters. So x0 is 10 centimeters. For v0, now we go to the second graph. At t equals 0, the velocity was at negative 4.58. So it's negative 4.58 meters per second. xm is the maximum amplitude, which is this one, which indicates that it is 25 centimeters. Now, Vm So we go from the equilibrium position to the maximum value. So it is at 5 meters per second. This is the solution for this part. Okay, deduce that omega 0 is approximately equal to 20 radians per second. To solve for this, we will make use of what we found before. I will solve this in two methods. The first method, we found that xm is equal to square root of x0 squared plus v0 squared over omega 0 squared. Square both sides because we are looking for omega, which is under the radical. You will get xm squared is equal to x0 squared plus v0 squared over omega 0 squared. Rearrange the formula to find omega 0. You will get omega 0 squared is equal to v0 squared over xm squared minus x0 squared. So omega 0 will be equal to radical of this. I will replace the values directly. Negative 4.58 squared over xm was 0.25 squared minus x0, which is 0.1 squared. Then omega 0 is equal to 19.98 radians per second, which is approximately, they said approximately equal to 20 radians per second. This is the first method. Another method that we can use to solve is the following. We found the formula for v as the first derivative of x as xm omega 0 cosine of omega 0 t plus phi. For v to be maximum, then cosine omega t plus phi should be equal to 1. For vm, cosine omega t, omega 0 t plus phi is equal to 1. Then Vm is equal to xm omega node. Instead of this, we put 1. I'm looking for omega 0. It's equal to Vm over xm. Vm, we found it as 5. Xm, we found it as 0.25, and this results in 20 radians per second. So we can solve it either way. Number 9, we repeat the same experiment by replacing the block S of mass m by another block S prime of mass m prime, which is 0.8 kilograms. So we change the block to have a different mass. The new proper angular frequency omega prime is equal to omega 0 over 2. Part A. Write the expression of omega prime in terms of m prime and k. Okay, we know that omega was equal to radical k over m. Now, the same thing, omega prime is equal to radical of k over, instead of m, we put m prime. This is the solution. Deduce the values of k and m. Okay, first of all, let's find omega prime. It's given as omega 0 over 2, so it's equal to 20 over 2, which means that it will be 10 radians per second. But omega prime is equal to radical of k over m prime. So let's replace, I'm looking to find k. So omega prime squared is equal to k over m prime. Then k is equal to omega prime squared cross multiply multiplied by m prime. Let's replace k is equal to 10 squared, omega prime we found it as 10 squared, multiplied by m prime, which is 0.8, and we will get k as 80 newtons per meters. We found the stiffness or the spring constant k. Now, we have to find the value of m. From the previous part, we know that omega is equal to radical k over m. This is omega 0. So if I wanted to find m, let's square both sides again. Omega 0 is equal to omega 0 squared equals k over m. Then m is equal to k over omega 0 squared. Then m is equal to 80 over 20 squared. This means that the mass is equal to 0.2 kilograms. So we found k and we found m.